Let's work through an example, an old example, the partitions of a number. A partition of a positive integer n using parts up to size m is a way in which n can be expressed as the sum of positive integer parts up to size m in increasing order. So if I want all the partitions of the number 6 with parts up to size 4, then I get all of these different options. I can add 2 and 4 together, or 3 and 3 together, or 1, 2, and 3, but I don't use any 5s because I said the maximum size of a part was 4, and all of these sum up to 6. Once upon a time, we counted the partitions of n using parts up to size m, but now we're going to construct the partitions themselves, which sounds more interesting. So the structure I have here, which lists out 3 different base cases, where the first one says that if I subtracted m from n and got exactly 0, then that counts as one of the ways of partitioning n, which basically means that if n was 3 and I used a part of size 3, then I would get 0, because one way to make 3 is just the number 3. Well, we can write it this way, but there's another perfectly good way to write it, which is to look for an exact match between n and m. We're counting up the number of ways of partitioning, so by default it's 0, but if it's the case that m exactly equals m, then we have an exact match. So that's one of the ways of partitioning n, and we'll just add it in here. And then, since both of these cases return the same thing, let's just put them together. If n is less than 0 or m equals 0, then there's no more work to do. And let's just make sure this still works. It does. At least for this example. So now we want to talk about not counting the partitions, but listing them out. If I list the partitions, I want lists like 2, 4 is one way to make 6. And it's going to return a list of lists. If we can't partition n, then that list would be empty. The list of ways of building this using an exact match would be empty, unless it's the case that I found an exact match, in which case I want to have a one-element partition of n. With m means that my partition actually includes m, so I need to make sure that the result actually has the right format. This is a list of lists. I go through every element in that list, and what I want to construct is that element with an m on it. Without m, I need to call list partitions because I changed the name of my function, but since none of these partitions include m, I don't think I need to change them at all. Then I sum these 3 up in order to build one long list, and let's see what I got. I got a list of lists of partitions. Let's write this out in a way that is easier to read. For p in the list of partitions, print p, and we get all of the partitions. I have yet to use yield. Instead, I've used a list containing a list with one element, or an empty list. And here I've built a list comprehension where I had the old list and I put in another list. It's a lot of list manipulation. And what if what I really wanted was a list of strings, where instead of 2, 4, it would say 2 plus 4, etc. How would I do that? Well, there's still a base case that says there's no such string, but here, instead of building a list with m in it, I'll build a string with m in it. And when I want to append m onto an existing partition, well, that would involve building the right string. And what do we get? A nicer formatting for the same result. So all of this is possible using lists, but I think it's simpler using yield. Let me show you. If I want to yield all of the partitions and get exactly the same result, instead of building up a bunch of small lists, I just yield their elements. If n equals m, I yield not a list containing stir m, but just stir m itself. I just think about the elements as opposed to how to put them into lists and combine lists. I just say one of the ways of partitioning n using parts up to size m is just m if n equals m. In fact, I don't even need this anymore. Now there's a lot going on in this line. Part of it is that I want to go through all of the partitions of n minus m. But when I'm writing a generator function, I just think about what to do with each one. No list comprehension necessary. I just want to build a longer partition. What do I want to do with all the partitions of n? Using parts of m minus 1 or smaller. Well, those are all partitions of n using parts up to size m, so I'll go ahead and yield from that. And what do I return? Nothing at all. I'm finished. And in fact, this return value isn't doing anything at all. I don't even need this base case. I could just say if n is greater than 0 and m is greater than 0, so there's some hope of making progress here, then I yield a one-element partition if that makes sense. Otherwise, I build up longer partitions by subtracting m from n, and in addition, keep all the partitions of n using parts up to size m minus 1. And this is the result that I get. I think this version is not only more elegant and easy to read, once you get your head around what yield means, which is to contribute one element, and what yield from means, which is to contribute a whole group of elements to the final output. It's also very efficient in that it's doing the same computation, but if you only needed to do part of that computation, this would stop early. So let's say I wanted to partition some big number like 60 using parts up to size 50. Assuming I could spell, this would take a while because it's considering lots of different possibilities. Almost 1 million of them. But if I didn't want them all, I just wanted, an example, then that would happen really fast. If I wanted 10 examples, that would happen really fast. That's only true of the version of this implementation that uses yield. The previous version, which had lots of different list manipulations, was forced to build the whole list of 966,000 options before I ever had a chance to look at the first 10. So if you're ever writing a program where there are many possibilities and you only want a few of them, sometimes this generator function approach can not only be easier to write, easier to read, but also dramatically faster to run.